Okay, next talk from Shiv. Stateful applications, zero downtime on this stuff. And so that you don't get confused. But it's not important, otherwise it would be in big letters. Go for it.
Thank you. So I'm really excited to be here. This looks like a really great audience, and I see a lot of DevOps folks here. And that makes this extra special because this talk is about what's finally possible for stateful workloads on Kubernetes, right? And the idea that we're going to introduce is this idea of container state replication that's going to make this possible. So what are we actually trying to achieve here, right? The talk is titled Mastering Zero Downtime, Container State Replication for Seamless Migrations on Kubernetes in footnotes. What does that actually mean, right? In a nutshell, we're trying to achieve true zero downtime migrations between nodes for stateful workloads on Kubernetes. So let's break that down a little bit. What do we define as stateful workloads? Kubernetes is designed for ephemeral or stateless workloads. And so you can think of these things as like microservices or serverless functions, CDNs. Basically, anything that doesn't store information in memory, you can consider that to be a stateless or ephemeral workload. And so, your HTTP microservices or your serverless functions, they have the option to go and query a stateful service like a database if they actually need any stateful information, but generally they don't store any of that information themselves. And this is, largely a function of the HTTP protocol, which in itself is stateless. And what makes stateless services so special is that HTTP load balancers allow you to scale instances up and down quite freely. So you can just spin up 10 copies of your workload, and even if you have a client connected, we can just direct requests to different instances without really breaking anything. And that's why I was so excited to see so many DevOps people here today, because I think everyone will agree that all of the infrastructure operations that we do on a day-to-day basis are easier when you're dealing with stateless services. The problem is that somewhere, no matter how much you try and hide it, there is state. And as we move more towards stateless services, those stateful systems end up siloing in these kind of points of pain that we see throughout infrastructure. And so if you think about it, okay, you can scale your stateless service up and down, but how about scaling the load balancer itself, right? How about creating 10 copies of that load balancer in different regions? Can you migrate customer connections between those load balancers really easily? The answer to that question is no. So you've pushed your state, your connection state, away from your application, but you have pushed it somewhere. You haven't gotten rid of it completely. And so some workloads that are stateful by definition are like databases. And so the in-memory databases are kind of the obvious approach, but also transactional databases where any uncommitted transaction is state. And yes, you can disconnect a client, and yes, you can roll back a transaction, but at the end of the day, that's not ideal. That is not how your database functions in the ideal scenario. So that is state. And then we can kind of zoom out a little bit and look at TCP connections in general. So TCP connections are stateful. Right? And so anything that lives on top of TCP connections where the application layer protocol doesn't hide that away, so HTTP is stateless, but it lives on top of TCP, and Quick can now do UDP. But generally, the protocol itself was designed to hide the fact that the connection layer is stateful. If you're not doing that, so Postgres' wire protocol is a good example of this. Game servers are a really, really painful example of this. VoIP services are an example of this, where the actual connection state matters almost more than what the application is doing at any given time. So the main thing you should take away from this is that stateless workloads are easier to work with, but stateful workloads are the ones that we really have to deal with, and that's kind of why we're focused on them for this talk. So why do we want to deal with migrating these stateful workloads? Why is it important for us to be able to migrate them more easily? And the answer to that, roughly, is because it's hard, okay? Migrations on stateful workloads are the ones that result in downtime the most often, right? Disconnected clients, I talked about that, is the biggest one. But also when you have services that maybe don't have a lot of network connectivity, like data pipelines, where you have a bunch of jobs, the state of that job before it's finished and commits that result to memory is state. And so you're going to have to repeat that work if you try and migrate those jobs away. And that's not ideal for really long jobs or very large jobs. And so the idea here is that downtime can take many forms, but the key is that even if a client can reconnect, even if the work can be redone, there is a cost associated with doing a migration. And then building on that, scaling stateful workloads is difficult. right? So workloads that are stateful can often become stuck on the physical nodes that they start on. And so if you think about this, a good example of this is like a game server. Think of like a Minecraft server or like the Fortnite game server that Epic Games uses. If you have a bunch of players connected to that server, that not only does that server has in-memory state, but it's also constantly communicating in real time with all of these connections. If you have one game server on a massive node, you have to wait for that game to end before you can do any moving. Otherwise, you're going to have disconnected clients and you're going to lose game state. There's kind of like, it's very, very difficult to get around that problem. And then, of course, synchronizing state between new instances is hard, right? We're going to look at this with Postgres' write-ahead log in a bit, but generally speaking, when you synchronize state between two stateful services, you have to keep them up to date. And that's very, very difficult to do without slowing down your application. It's very difficult to do asynchronously. And then finally, risk. When you're scaling stateless services up and down, like there's no state to lose. There's no damage that you can do. There's damage that you can do, but generally speaking, like there's not a lot that can go wrong compared to when you try and move a database, for example, right? What happens if you lose state there? Obviously, you're going to have disconnected clients, but that's, you've already accepted that. What happens if you lose additional state on top of that? Okay, so now we know what stateful workloads are, and we know why it's important for us to be able to migrate them easily, but what do we mean by zero downtime? So let's say you have a stateful workload. Let's pick Redis, it's my, or Valkey, that's my favorite one. And it's running somewhere on some Kubernetes node, and I want to move it to a different node, okay? Whether that's because I want to do maintenance on the node or because I want to move it closer to my users, for whatever reason, I want to get it off of node A. My goal is that I have to do this without any downtime. So obviously the application can't lose any state, so that's just a given, right? I don't want to lose any data. But on top of that, like the application itself shouldn't notice that the migration has occurred. And then if we're sticking with that zero downtime theme, the client shouldn't notice that the migration has occurred. So the client should stay connected, and you shouldn't need to modify the protocol to be able to do this. It should just work out of the box. That's the key part for this infrastructure. So you have to preserve network connectivity. And then the question is like, how far can we actually take this, right? So can we do this between regions? Can we do this between cloud providers? Can we do this between continents? Or can we do it between all three of those at the same time? Okay, so we want to move any application. We want to move it from anywhere. We want to move it to anywhere. And we want to move it without any downtime. Before I go any deeper, I should explain who I am. My name is Shivansh Vij. I'm the founder of Loophole Labs. That's my Twitter, Confused Qubit. You can hit me up there if you have any questions. I'm Shivansh Vij on Blue Sky as well. And then if you have anything you want to talk to after the talk, you can hit me up on LinkedIn or GitHub, both of which are just my full name. So what's Loophole Labs? We allow you to take advantage of spot instances for any workload on any cloud provider. The idea is that we save you 90% on your compute costs by taking advantage of those spot instances for even your stateful workloads like databases, CI/CD, data pipelines, game servers. And we can do this thanks to our live migration tech. What I'm going to be talking about today, the idea is that when a spot instance gets preempted, you get a 2-minute warning from AWS. What we do is we take that warning and we just move your app to a different node, right? We just move it to a different instance. And because we can do that migration really quickly under that 2-minute warning and without any downtime, you get to take advantage of spot instances without having to worry about the usual headaches that come with them. So you get the cost savings without having to worry about the problems. So those are our socials for Loophole Labs. You can get in touch with us after the talk if you want, if you're interested. Okay, so stateful application migration generally comes in 2 categories, right? And the first category is application layer replication. And a good example of this is Postgres' write-ahead log, but also Cassandra's node replication. And so let's actually take a look at this for a second. So imagine that you have a client connected to this magical Postgres router. I'm hand-waving it away, so imagine it's just as magical as an HTTP load balancer is, right? It's able to handle all those state. And you have a Postgres instance running on node A, and every time your client commits a transaction or does anything, your Postgres database writes that data to the write-ahead log, okay? Now, application layer replication is when the application data, in this case the write-ahead log, gets replicated to a different node. Okay, and the application has to be designed to support this. It has to be designed in such a way that all of the state that it actually accesses during a normal operation is queried directly from the application data. So the idea is that like nothing in memory matters to Postgres, right? That's why transactions are a thing. If you don't commit the transaction, it doesn't matter. And so this kind of transactionality ends up being a consequence of this design requirement that we want to be able to do application replication, where we move the application data from node A to node B, and then we can redirect your client, right? That magical load balancer can just redirect your client, and the next transaction that happens, or the next database query that happens, will hit the write-ahead log. So that's kind of your application layer replication. That's kind of generally how you do stateful stateful migrations. But again, your application has to be designed for this from day one. Your client, your protocol, everything has to be designed to support this. The other category is more general, and we can kind of put that in like live kind of workload migration. And so instead of replicating the application data, what if you could, and pointing a new instance of your app to it, what if you could actually move the app itself? And the hard question that we need to answer is like, where is the boundary of your application in that scenario, right? If we're gonna pick it up and move it, we gotta know where the edges are. And so VMware did this first, and they did it using VMs. That was their boundary. They said the virtual machine is the boundary. We have this thing called vMotion. It's 21 years old at this point, and we're going to be able to pick up your VM, and we're going to move it from node to node. Then there was KVM. There we go. Okay. Then there's KVM, right, which also is VMs. There we go. And this is what most Linux hypervisors use today, and it's a really popular front end for this is QEMU, and that has live migration built in. And then there's CRIU, which is checkpoint restore in user space. This is the most interesting thing for us because the boundary in that scenario is not a VM, it's a process. And in our case, that's a container, okay? So a container is just a process if you squint. And you don't have to squint all that hard. So, but the problem is with all of these solutions, it's that none of them actually fulfill our requirements, right? The application layer solutions aren't generic, so they're not gonna work for arbitrary stateful containers. vMotion is cool, but you gotta buy into VMware and now Broadcom's entire ecosystem, and then you still have to run everything on premise. So it's just not practical. KVM is great, okay, but it's not zero downtime. It's live migration, but it's not zero downtime. Your clients are going to get disconnected during a migration, not to mention the fact that there's actually a serious performance hit during the migration as KVM is trying to, or QEMU in particular, is trying to like track the state of your application. And then CRIU is the same. Like all it's doing is checkpointing and restoring your application. It's not zero downtime, and of course it doesn't keep the network connections alive either. So what we need is a new solution. So what we need is a new solution, and one that builds on kind of this general live migration solution that came before. And this solution has to be hypervisor agnostic, okay? Right now, we're able to migrate like VMs around, and the thing that Loophole does is we migrate micro VMs around. So we put your container in a micro VM, that's our edge, we proxy the Docker socket out, and so like from the perspective of Kubernetes, it's looking at a container, but what we migrate is the full VM. And that's a lot easier to do because the boundaries of a VM are very well defined. I can just move the kernel and the app. When you try to move a process, it's very, very difficult. You kind of have to tear it out of an existing kernel in the middle of a syscall maybe, drop it into a new kernel, and then somehow stitch everything back together. It's very difficult to do. So it's always easier to move a VM than a process. But eventually, we want to do pure processes. In fact, we have to do pure processes. So the next requirement is zero downtime. And this is a really special requirement because it's the time during which your application isn't running and it's not servicing clients. It's not just the disconnected clients, but it's the time that your app is actually down. Generally, any migration happens between point A and point B. At some point, you have to stop the app on point A, on host A, and then start it on host B. And the time between stopping on host A and starting on host B is considered your downtime, assuming that you can magically get all the networking hooked up instantly. QEMU has live migrations built in, like I said, but they're not zero downtime because the time between stopping and starting can be quite high, tens of seconds to even minutes sometimes. The same goes with CRIU. It's just checkpoint restore. So you're checkpointing, then you're copying the entire state of your app to a new VM, and then you're restoring. And so that entire copy step, your app is down, it's not so. That's, again, assuming that you're magically reconnecting the network, which is obviously very difficult to do. And so the last requirement, which I keep saying, is we have to also be able to migrate network connections, arbitrary TCP or UDP network connections. This is a hard requirement because, again, we want to work for arbitrary workloads. We don't have to want to write a custom magical Postgres load balancer or a custom application-specific load balancer every time there's a new app. So it has to be generic. And we generally want our kind of like zero downtime to be like under 500 milliseconds if we can get it. We want to get close to 200 milliseconds. So the time between stopping your app and starting it should be 200 milliseconds in your worst case. Now we internally have seen like better numbers than this, and we've seen worse numbers than this. Well, I'll talk about it in a little bit, but generally speaking, if you can get to 200, your app and your clients don't really notice. That's a network blip, right? Okay, so even though my app is stopping on host A and starting on host B, Even though the IPs are changing, the network routes are changing, all this is happening, we have to keep network connections alive, and we have to have all of this happen in 200 milliseconds. Okay. How? Container state replication is the key here. And the thing that I want you guys all to take away from this is that we want to move arbitrary containers, and to do that, we want to reduce the amount of time that the workload is stopped. That's the key optimization here. Anything we can do to reduce that amount of time, that's what's going to give it zero downtime. And so the way that you do this is by being able to continuously serialize the state of your container in real time, asynchronously, without affecting its performance, and move it to a different host. Before you actually have to stop it, what if you could move most of the data, most of the state of your container? It's really difficult to do, but if you could, that would solve a lot of the core issues. So we can actually split any live migration into 3 distinct stages. First, it's the pre-copy phase, which takes place before any sort of migration occurs. So if we think back to our Postgres example, like there's no way that we're going to be able to instantly copy the write-ahead log. Like write-ahead logs can get quite large. And so the idea is that during this stage, you copy the memory for your VM, you copy the disk for your VM to a new node without interrupting it, right? You're serializing the state continuously, and you're moving it to a new node without interrupting the application. So your app is still able to modify its VM, it's able to keep chugging along, but you're able to move, a good chunk of your app. The problem that comes with this phase is that, like, by definition, the data is out of date, right? The moment your VM modifies that data, that memory, anything that we've synced before is considered out of date, and we can't get it in real time because that would affect the performance of your VM. So we have a bunch of data on a new node, right, in the pre-copy phase, but we know that it's out of date, and we know that we can't actually resume your VM off of it. But it's important. The next step is where we actually start and do the migration. This is what most people call the stop and copy phase. So during the stop and copy phase, you're generally stopping the VM, you're copying whatever data you weren't able to send over, and then you're starting it. But again, that's not a constant value. We don't know how much data there's going to be. When in the previous slide, I said that we wanted our migrations to be zero downtime even under high load. What I meant was that while your application is generating additional data, more data than you're used to, you're still supposed to be able to do that migration. But in that scenario, your pre-copy phase isn't going to be very useful because a lot of the data is going to be changing, and if you're going to be limited by your bandwidth. So you're kind of limited by the stop and copy phase in that, like, downtime is how much time are you going to take to move that data. And so how can we get around this problem? Well, at Loophole, we started looking at this and we said, okay, well, what happens? What do you actually need to resume a workload on host B? Like, do you actually need that dirty data? And the answer actually is no. You actually don't need the VM's memory to resume. You just need the program counter, you need the CPU state, and you need a couple process registers. Really all you need. If you have that, you can actually resume the workload on host B. The problem is when it does resume, it's going to try and read that data that you didn't send. That's where the third phase comes in, which is the post-copy phase, which is where your application, during the stop and copy phase, let's say you didn't move any data, you just sent the CPU registers, which is very, very small, like kilobytes. And then you went and started the application, and you're now in the post-copy phase. Every time your application tries to get some memory or tries to read the disk, you can go and fetch that data on demand, either from like a persistent store like S3, which has high latency, so there's trade-off, or you can fetch it peer-to-peer from the original host, right? So you can, so that's kind of generally how these are implemented. But like I said, that's very latency sensitive, right? Imagine that your application is attempting to read a stack variable, because it's a VM. We have to go and fetch it every single time, 100 milliseconds. So if you implement this badly, you get a significant performance hit after the migration occurs. Okay, so we have to mitigate all of these issues. And this whole game, I'm sure you guys will realize, is a game of amortization, right? How much work can we do before, after the migration, so that we can shrink the actual migration time down to as little as possible? This library that we put together to do all this is called Silo. It's completely open source, including the kernel modules that we use to read the state of your process or your VM without actually interrupting its performance. All of that is available in there today, and you guys can go and integrate it. Okay, so how does Silo actually work? It starts with a pre-copy phase. As part of the main part of this is what I've been referring to as container state replication. This is like the brunt of it, right? This is the main part of the amortization. We want to asynchronously replicate the state of your container, your process, to either an active host, so like just like the host that you're going to be sending your application to, or to like a passive system like an S3 bucket. And we want to be able to do that without interrupting your app. Now, Silo builds on this stage by getting really, really smart because it can see what parts of your application and disk are changing as they happen. And so Silo can quickly come up with a profile or like a heat map where your application is the hottest. So it can quickly figure out exactly what parts of memory your application is like accessing and modifying more often. And it can optimize moving and synchronizing the parts of memory that are least likely to be written to first, because those are the ones that are least likely to have to get overwritten. And so the idea is that if we can sync these bits up to an S3 bucket or in advance to the receiving host before we need to stop your application, then we'll be able to see generally a 70 to 80% reduction in the amount of data that we have to move during the stop and copy phase. So you'll be able to get 80% of your container state off the host before you even have to do a migration. And that's really, really key. All right, then there's the stop and copy phase. But like we said, the copy part, really bad. We don't want to do it. So why don't we rename this to the stop and start phase? In this phase, we're going to move the bare minimum amount of data. Because Silo knows which blocks of data it has already synced, and instead of sending that data it hasn't synced yet, it's just going to give us a manifest of those blocks. And so that allows us to send the CPU state, the process registers, and a manifest of all the dirty data over to the new host. And so we don't have to send the data itself, just the manifest, which significantly reduces that copy time that we were talking about. Now our application can resume on the other host, and it's going to try and access that data. Now this is where we take advantage of Silo's post-copy phase. Because the application is going to try and access this memory or disk, and we can access that with Silo, again, this is part of the kernel modules that we put together, we can do all of this in kernel space. So your application can have a instead of using user fault FD or something else that has to jump up into user space over and over again for every 4 kilobyte page, you can actually do this completely in kernel as part of the standard page fault. Because you can do that, and because of the fact that Silo already knows what parts of your application are hot, Silo can actually go and trigger the fetch request from the remote host or from S3 before your app even requests it, because it knows what parts of memory it has to prioritize getting first. It can do that in real time. Okay, so that's a lot of talking and a lot of theory, but how does this actually work? Can we move arbitrary VMs between nodes without any downtime? So here's the deal. My colleague Felicitas is going to be giving a much more in-depth version of this talk during the actual conference on Wednesday. And she'll be showing off like our production-ready open source Kubernetes integration, which is tailored specifically for spot instances and multi-cloud migrations. She's going to actually migrate an entire Kubernetes cluster between like Azure and AWS and GCP, like in real time on stage while the microservices are talking to each other. It's bonkers. So I thought instead of giving everybody the same demo twice, why don't I show off one of our R&D projects? You remember when I said that we eventually wanted to move pure processes? So that's what we're going to demo. It's not a full Kubernetes integration yet, which is why the Kubernetes part was in brackets, but I thought it would be less boring if you guys got to see something that's a little more experimental that takes advantage of some of these techniques, right? We said they had to be agnostic. Let's prove that they're agnostic. Okay. So let's hope the live demo gods are with me today. So I've got a couple screens here. On the top left, I'm going to start a Docker container. You're going to see I'm going to run Docker PS. This is a shell script that I hacked together that just starts the Docker container. It hijacks the kind of run command to like put in all of our hooks so that we can start tracking all the memory in the kernel. And then it just starts a bog standard Postgres instance. So let's click this. And we can see, there you go, everything is started. So we use the Docker entry point. I'm just using Docker, but you can use like Podman or whatever. It doesn't really matter here. And so I've just set the Postgres password to password. And now I want to be able to migrate network connections, right? So I'm going to tell Loopholes Network that we have a fresh port, which I need to CD into the right repo for. There we go. There we go. OK, and now we have a network route. So in theory, we should be able to connect. Good. All right, we got a Postgres database. Let's go and let's start by creating a table. And then let's actually begin a transaction. All right, so now we're in the middle of a transaction. Let's apply a change. Insert into. Good. Now, we haven't actually committed this transaction yet. Now, let's actually go and migrate this. So to do a migration, first we want to move the network connection. Now, again, I'm doing this manually, but this is normally done by our control plane very, very quickly. There we go. Okay. So what I'm going to do is I'm going to change the network connection. I'm going to trigger the migration. So this host here is a different host on AWS. So we're going to move the Postgres instance from host A to host B. I'm going to move the network alongside it. And then I'm going to commit the transaction. And I've actually never tried this before. I usually do this without the transaction part. So like fingers crossed that this actually works. All right. So let's. All right. We've updated the network routes. We're ready to receive them. We're going to trigger the migration. So again, there we go. Of course it was going to break today. Error connect. Oh, I know what I did wrong. Sorry, I forgot to start a separate process here. Okay, all right. So we have Docker PS. Look, it's running Docker. This is why this step is here. So I'm supposed to show you. We have got a Docker process running. We actually have to go and dump the Docker process, or get ready to dump the Docker process. So I've got our little kernel module is going to load up, start replicating the state. Now it's ready to move. And now I should be able to do the, oh, sorry. Okay. Now I should be able to do the move. Perfect. Everything has moved over. So we've moved Postgres. Now, in theory, I should be able to type in commit here. And my existing transaction should complete. But not just my existing transaction, but my existing TCP connection should still be alive. Worked. Okay. So now let's see if I can. There we go. And that's it. So we've moved a uncommitted transaction, pure processes, pure Docker, no VMs involved at all, between two nodes. We kept the network connection alive as well. Okay. Glad that went well. I have time? I have 5 minutes. Okay, perfect. Okay, so thankfully the demo worked. So we really can move any application around, right? Felicitas will show you guys how we move VMs around. It is much more impressive than what I just did because there's a dashboard and there's a UI. It's all very nice. From anywhere to anywhere, right? So we just moved it, and we did it without any downtime. The client couldn't tell that the migration had happened. And the best part is, like, all of this implementation is completely open sourced. You know, you can go and integrate Silo into your workflows today. It'll be a few months before this like pure process migration stuff is ready for prime time, but you can actually go and migrate VMs on Kubernetes like today with a project that Felicitas is doing called Drafter, and it's an open source VM migration primitive that like integrates with Kubernetes, and it uses Silo under the hood naturally. And so the key takeaway here is that like zero downtime migrations for stateful workloads is here now, right? And I think it has the potential, hopefully, to change the way that we deploy infrastructure. You really can move any application from anywhere to anywhere. Postgres is a really painful app to move, especially along with its various like weird memory mapping nonsense that it does. And with that, we're done. All right, thank you for sticking with me until the end here. And I think I have a couple minutes left for questions.
We have, yeah, a few questions.
Perfect.
Anybody? Oh, let me go.
Thanks. I just noticed your demo script there was using checkpoint restore and user space there.
Yeah.
Can you talk through sort of what you were doing on top of that, or?
Yes. Okay. So the thing with checkpoint restore is, while it's very, very good at checkpointing the application, it is very, very bad at tracking the actual like memory usage of the application in real time. It can do it kind of well using user fault FD and on x86, but it's really it genuinely can't do it on ARM. And so our biggest change that we made was we've built a layer on top of CRIU, so we can't actually modify CRIU directly. It's C code. It's a pain. So we built a layer on top of CRIU, which is kind of what that shell script is wrapping. It's called Mason. You'll have seen like references to it. And Mason is to processes what like Drafter is to VMs. It effectively takes CRIU, patches the parts that need to be patched, adds the layers that need to be added on top of it, so that when you go and try and do a migration on a container, not only are you able to actually migrate the process, like we treat it like a real process. And that's really key because it means you can move from Docker to Podman. You can move from run C to somewhere else, and it just works because it's just a process under the hood, right? But then more important to that is the fact that like we're able to control the network connections. There's a lot of eBPF code behind the scenes here that is actually tracking and rerouting connections in real time in the lowest latency way possible. And then of course there's the actual like memory tracking. So we have to do that in the kernel. We can't rely on like the user space applications because they're just really slow. It's just a kind of a pain to do.
Okay, yeah, thanks for the explanation. Is Mason available on GitHub somewhere I can have a look at?
It's not open source yet, but I'm happy to talk to you afterwards if you'd like to get some sort of access to it. Yeah.
Thanks.
Anybody else? Yeah.
See now, if you want to migrate inside Kubernetes from one node to another node, See, fundamentally, you have scheduler and the etcd, which is like, hey, I have
Yep.
this many pods here and all those things, right? And under the hood, if you keep moving all these pods here and there, like then how will etcd keep?
Yes. So that's a really good question. And I would say that like as cool as our live migration tech is, the way that we solve that problem is even cooler. We just don't mess with Kubernetes. So we want to be able to support all the different Kubernetes schedulers and all the weird things that they're doing. And so all we do is we hijack the deletion request that comes in. So we have a containerd shim that we install on your nodes. And so when you try and move a pod, what does Kubernetes try and do? Because it thinks everything is stateless. It says, I'll delete it here and I'll recreate it over there. So we just add a label to your pod spec before that deletion happens. And then when the deletion request comes in, we just look for that label. And if that label is there, we lie to Kubernetes and we say, hey, it's deleted, wink, wink. And then Kubernetes goes, great, that's good enough. I'm going to schedule the pod on node B. Then the pod gets scheduled with the same label. And then we get that create request, we look for the label, we go, oh, great, so this is a create request. I just saw a delete request. I'll migrate the state in the background. And then once the migration is complete, then I'll actually delete and give Kubernetes the thumbs up, and I'll actually tell Kubernetes the pod started. So when you do it this way, it doesn't break any of the cloud native conventions. The CSI gets mounted correctly, the CSIs get mounted correctly, all of the data that you expect to be there is available there. There are 3 questions now. I might have confused more people. 4 questions now.
Last one. Who was the first? You? There you go.
Does that still play if that pod has things like an init container? Because Kubernetes is going to expect to see that init container complete. Do you lie to it that the init container ran and completed?
So there's a flag that so it's not as generic as I would like it. There's a flag you have to give us. If your init container actually has to do something important every single time, then you can add that flag and we won't lie anymore. But generally, we do lie. Now, with VM migration, it's a little bit easier because we just move the VM and all of the containers in your pod move along with it. A little bit more annoying when you're moving the individual processes because now you got to create a process tree and it's a little bit more annoying. But yes, so generally, it's a flag that you can build in, right? And so if you're doing something special and you want it to run every single time, fine, we'll run it every single time, right? Not a big deal. But generally, we found that for most workloads, the init container, you can just kind of lie to Kubernetes and it's fine, right? Because the state is the state, right? You've already moved the state, so whatever it was doing, assuming it wasn't reaching out to an external service, whatever it was doing is still done, right? So it generally speaking, the compatibility we've seen is quite high. I haven't actually found a workload that got angry, but I guess we'll see.
Okay.
Okay.